Hello and welcome back to the solution videos for the Marquette Programming Competition. We're on to question 8 now, the last question in our competition, and this one's a little bit harder. It's the hardest one in our competition, so to start we're going to just kind of go over what we're going to do in this video, and then we'll actually go and do the implementation. So first of all, the 8th question is asking the students to write a program that determines the number of ways to fill a given size rectangular grid with triomino-shaped pieces. So here's an example right here. We've got a 3-row by 2-column grid, and there's 3 different ways that you can fit these pieces up here at the top, which are each made up of just 3 squares, just attached to each other, onto the grid. You can stick the 2 angles together in 2 different ways, and then you can also have 2 vertical bars. Those are the only 3 ways that you can fit 3 unit sized pieces to fill this grid up, with no overlap off the grid and no missing pieces on the grid, or missing squares on the grid. So that's the task. We have to be able to do this for any size grid up to 8, I believe, is the maximum. So we're going to be doing our solution in this skeleton right here, count triomino's fittings, and it'll take in the rows and the columns that are the size of our grid. Alright, so before we get started, the way that this video is going to work is there's 2 essentially parts that we'll have. We'll have our scanner solution, which is the way that we're actually going to be doing this problem and figuring out the number of ways to fill a grid with triominoes. And then the second part will be using a dynamic programming technique called memoization to make our solution faster. So the reason for that is what we need our solution to do, essentially. Our solution has to make sure that it doesn't count any invalid solutions, so any solutions which are missing a square, or any solutions which overlap, like off the grid, or overlap with other triomino pieces. We have to make sure that our solution correctly only counts valid solutions. We also have to make sure that our solution counts or doesn't miss any valid solutions. There's a lot of ways to do this, but if we miss one, then we have a number that's fewer than the actual number of ways to fill it up. In addition, this problem is quite hard. Once you get up to high grid sizes like 8 by 8, there's millions of ways to cover the grid with triomino pieces. So the solution needs to be able to run in a reasonable amount of time. We can't be sitting here for a minute or 2 minutes just waiting for our program to finish executing and output our solution, especially on the competition. Alright, so with that, let's go into our solution. So first, let's just outline how this is going to work. So the scanner solution is going to have this sort of scanner object, which is going from left to right, top to bottom, across the grid. So it'll start in the top left corner, and then work its way across, looking for empty spaces. So at each space, if we find an empty space, then we're going to go through all the triomino pieces and try to place them there. So we'll loop through each triomino piece. We'll try to place the piece. If we are able to place the piece, then we'll advance the scanner off to the next empty space. Essentially, we're looping back to the top of this, where we'll continue scanning left to right, top to bottom, because that means that we successfully did it and we want to essentially recursively do it again. So we need to find the next empty space, try to place it there, find the next empty space, try to place it there. So we're going to be using actual recursion for our implementation of this. If we aren't able to place the piece, then we just go on to the next piece. And then finally, once we run out of pieces, so once we place that last, or attempt to place that last horizontal black bar piece, then we'll go back to the previous piece. So this is recursion, so this will go back to the previous piece and then continue on with the loop there, either going on to the next piece at that spot or maybe going back even further. And this will all be shown visually in just a minute. Alright, if the space is full though, continue scanning. And then once we run out of spaces, so once we get to the bottom right corner of the grid, then since we're only skipping over full spaces and we're never advancing if we are at an empty space that we can't fill, we know at this point that we filled all of the spaces. We haven't skipped any empty spaces, and we've checked every space to make sure that it's full. So the solution has been found. So we'll count the current solution and then back up one step. This will happen as we place the very last piece, and then we scan ahead. So then we find that the solution's been filled, so we can scan back to that last piece. So go back to the last piece and then continue that loop. And that's basically it. So I've got a visual aid to kind of show you how this works. So our gray square in the top left corner, that's our scanner. And then this is an empty 4-row by 3-column grid. So the very first thing it's going to do is it's going to loop through all of our pieces. So if you remember, we go red, green, blue, orange, cyan, black. It's going to go in that order as well. So first thing it's going to try to do is place the red. It can, because the red fits on that spot, and it doesn't overlap, it doesn't go off the grid. And then it's going to advance to the next empty space. So it'll scan ahead, oh, it's found an empty space, and then it'll try the loop again. So it'll try to place red, it'll realize, oh, red goes off the grid, so it's not going to be able to place red. Same with green, same with blue, and then yellow. Once we hit yellow, then we're actually able to place it without covering it. So it places it, keeps scanning ahead, tries red, can fit it, tries red, tries green, tries blue, and then it finally hits yellow as well. Alright, so we fill up the grid at this point, but the scanner still needs to continue on with the loop, so it's going to continue scanning ahead. And then finally we've reached the bottom right corner. So we know that our solution has been found, so we're going to count this current solution. You can see that up in the title bar here. We've added 1 to our solution count. And then we go back to the last piece, the place that we placed the last piece at. And we pick it up and then try the other one. So we'll try the last 2 in the list, the 2 bars, both of them don't fit. So then we go back and then try more pieces. So it'll try green here, and then it can't fill this spot. So instead of advancing on to, say, the next empty space, it's actually just going to go back, because this is an invalid solution, that means. Then it's going to try blue, and then it'll only go so far here as it tries to place green, etc., etc. You get the idea. So it'll keep doing this recursively until it has counted all the solutions. So until it gets back up to the top left with the red piece and attempts to place the last triangular piece, so the blue vertical bar. So it advanced to green there, but once it gets onto the 6th one, then we'll know that we found all the solutions. So one important thing that's been kind of implied here is that we've kind of picked a spot on each of the pieces that we're placing them at. So here's the list of pieces, and the gray square here is where the scanner, if the scanner is at a position, that's how it'll place the piece. So the red gets placed on the top left corner of itself, the green gets placed on its top left leg, the blue gets placed on its top leg, the orange gets placed on its top leg, etc., etc. The reason we picked these is so that all of the pieces always go below the scanner. They never angle up above the scanner, and that's so that we can make sure that we rely that the scanner, as it goes across, we can always assume that everything above the scanner has been filled up. That assumption is really helpful in making sure that once we get to the bottom right corner of the grid, we know that we've scanned everything in that last row, but we also know that everything above the scanner has been filled. And we haven't missed any solutions, because if an angled up from the scanner, then it would basically never be able to be placed there with that assumption, because we already know that the above solution was filled. So that's why we picked these spots on the pieces. Alright, so let's go looking into implementing this. So we know that this solution is going to help us because it won't count any invalid solutions, because the scanner will check every single spot, and it doesn't skip over any empty spots. It also doesn't miss any valid solutions, and this one's a little bit harder to prove, but we can kind of think about it and know that, yeah, it definitely doesn't miss any valid solutions, because we try every single piece at pretty much every single spot. Yeah. So this scanner solution will help us with these first 2 points. And we'll see later on that it will be kind of slow for some of the higher ones, and that's where the memorization will come in, just looking ahead a bit. But let's go and implement this in code. So this is the method that we'll be using, count triangle fittings. So it's going to take in the rows and the columns in the grid that we're trying to fit, and then it's going to return the number of ways that we were able to fit it. Now, I mentioned that we're going to be doing this recursively. And so we're going to treat this method here, count triangle fittings, that takes in 2 parameters, as a top-level call for our recursive method. So we're going to have a second method, which is very similar, but it's going to be able to take in a grid as well, a working grid, as well as the current state of the scanner. So this method takes in the current state of the execution. So at this spot, it'll have a grid, a two-dimensional Boolean array filled with trues. We're going to say that empty is for false spaces and true is for full filled spaces. So the grid will be completely full on this recursive call. The scanner position is on row 3, column 0, since we're going to be using zero-based indexing. And then this count triangle fittings is then going to return how many ways we found that we could fill it up. In this case, it'll be 1, because it'll reach the end of the grid and realize, oh, we filled up the grid, so we've done it. So yeah, this is going to be a recursive method. Actually, we'll just give it a new name, count triangle fittings rec for recursion. And then up here, we'll just do the recursive call really quick. So num fittings is going to be our recursive method. And it's going to start with a completely empty grid. So it's going to be rows by columns. And when you initialize Boolean arrays like that, it initializes them all to false. So false is empty, so we have an empty grid then for our initial grid. And then we want the scanner to start in the top left corner. So we're going to pass it row 0 and column 0. That way we know that we're at the right spot. All right, so what do we need to do at every step of the way? So we've received a grid and we know where the scanner is. This method's going to loop through all of the triominoes and try to place them at the scanner spot. And if it can, it'll continue on with that stuff that we laid out in this Word document over here. And then if it can't, it'll just continue on to the next triomino. It'll also do some checking for whether or not we filled the solution, or filled the grid and found the solution. So we're going to have a tally, since we're going to be looping through all the triominoes. So we'll just say triomino 0 through triomino 5. We'll do 0 through 5 for the 6 different triominoes. We'll make red be 0, green be 1, the order that was on the sheet. And then we're just going to go through all of them. So as we go through all of them, we're going to be tallying up the number of ways that we were able to find. So we'll call that ways filled, like that. It'll start at 0, and by the end of this for loop, it should be the correct number of ways that we're able to fill the current grid from the current position recursively. So what is it going to do for each spot? Well, it's going to try to place the triomino. And if it can, it'll do some more stuff. If it can't, it'll just pick it back up and move on to the next one. So we're going to have a method called try_place_triomino. It's going to be placing it into a grid at that specific position. And then we'll also give it the triomino number. And it'll do the placement for us. It'll change the relevant spots in the grid. So we'll write that method in a little bit. And if we do, then we're going to advance the scanner. We'll write all that functionality. Otherwise, we're just going to move past. We're going to say that try_place_triomino is going to, if it can place it, it'll place it. If it can't place it, it just won't try at all. It won't place it at all. So we won't have to actually pick it back up. We'll only pick it up if it actually succeeded in placing it. So you've noticed that I put this in an if statement. So the try_place_triomino is also going to return true if it could place it and false if it couldn't. So let's go write try_place_triomino right now. So it's going to return a Boolean. It's going to take in our grid, the place that we want to place it, and then which triomino we want to place it at. Alright, now, so the first thing that we need to do for try-placing triomino is we need to check all 3 positions that the triomino covers and check if they're empty. If they're not empty, then we have a problem. We also need to make sure that the triomino places aren't off the grid at all, so they have to be within the grid bounds. And then if both of those things pass, then we're going to place the triomino itself. So the way that we're going to do this is we're going to come up with an array of coordinates that our triomino is going to fill. And we'll call this positions, the positions that it's trying to fill. And there's going to be 3 of them because the triomino covers 3 different places. The first position is always going to be the scanner position. We know that our triominoes always cover up the scanner position, this gray box right here. So we can say the position 0 will be, and then we'll put in the coordinates here. So row and then column, just like that. Position 0. Then the second and third ones, we're going to actually have to write some code for each of the different types of triominoes. So let's start with the red one. So this is the, if you remember, the L shape, which goes to the right and down. It has a right leg and a down leg. So our, and we'll put this in a switch statement. So a switch statement is just a kind of simpler if statement. Essentially, we're going to be switching. We're going to have different code for each of the different triominoes. So we're going to switch on triomino. And red is case 0. So if triomino is equal to 0, then we're talking about the red piece. And if we're talking about the red piece, then we know that our first position, let's say, is directly to the right of the scanner piece. So on the same row, but 1 column more. Remember that our increasing columns are to the right, and then our increasing rows are down. Top left is 0, 0. Bottom right here is row 4, column 3. So this is on the same row, 1 column to the right. So that's going to be our first leg off of the scanner. And then our second leg is directly below. So in the same column, but 1 row down. So row plus 1, and then the same column as the scanner. Just like that. And so we just need to do these for the other 5 pieces. Alright, so I've gone ahead and done the other ones. So you can kind of see some of the complex shapes here. So the green one has 1 piece to the right of the scanner, but also 1 piece that's right and down from the scanner. So we've got on the same row, but 1 column to the right, and 1 column below, 1 row below, and 1 column to the right, all at the same time. Same with orange. Orange is a little bit different because we actually go backwards. We go to the left from the scanner position. So our second piece is 1 row below, but 1 column to the left. So these positions now, this array of 3 different positions, now has all of the exact coordinates on the grid that we need to check to make sure that they're on the grid at all, and we need to check whether they're empty. And then we need to set them to true if we're actually going to place this triomino. So that's what we'll do now. So we'll go through each position, which we can just do like that, and we're going to check whether or not it's on the grid and whether or not it's empty. So first of all, if position 0, if our position, the row is, okay, so this if statement we actually want to be checking if it's violating any of these things. So by the end of this for loop, we're actually going to have a flag here, valid position, we'll say. And we're going to assume that it's true unless, as we go through these positions, we find any violations. So then at the end of the for loop, we'll have the correct whether or not it's valid. So an invalid position will have an x that is, say, less than 0, or an x that is greater than or equal to our maximum number of rows. Oh, I'm sorry, when I say x position, I mean row position. So that'll be grid.length. Or, same with the columns. The column has to be greater than or equal to 0, and the column has to be less than our maximum number of columns. So we can say the first row's length is the maximum number of columns. Okay, we also need to have all these spots be empty. So the grid position at the current position needs to be equal to false. We need it to be empty. So actually, it'll be violating it if it's equal to true, and that's what this if statement is checking. So we're checking if position is violating our conditions. If it does violate our conditions, then we need to change this flag to false. Otherwise, we'll just leave it whatever it was before. That way, if multiple positions violate our condition, then both of them will just set it to false, and neither of them will flip it back to true if any of them are okay. So by the end of this for loop, we should have it checked that all of the spots are empty and all of the spots are on the grid itself. So then all we have to do is loop through all the positions. Oh, sorry. So if it's invalid, let's say, then we shouldn't place it at all. We should just return false. We should tell them we couldn't place your grid or your triomino, so we didn't. Otherwise, we'll go through all the positions and actually set them to filled in the grid. So we'll just say grid at the positions row and the positions column. We're going to set it equal to true, so filled. So we actually did do it. And then at the very end, we'll return true then. We actually did place your triomino. So this method will take in our grid, the place that we want to place our triomino, and the triomino type. It'll figure out all the different spots that it needs to check and fill using all this relative logic here. And then it will check if all of those positions are on the grid, check if they're all empty. If it violates any of those conditions, it'll just instantly not place it and return false. Otherwise, it'll actually place the triomino and then return true for us. All right, I'm just going to collapse that. So back up at our if statement. If it returns true, then we know that we have placed the triomino, and so we can advance the scanner and then do the recursive call. So let's do that part now. So we're going to have two variables for the next position of the scanner. So as we scan, we'll start at the current position, but we don't want to just change row, the variables row and col here, because since we're working with multiple triominoes, we want to make sure that we save that original position of the scanner. So this is essentially saving the original position so that we can go back after we tested one of the triominoes, which is kind of the motion that we saw here. So jumping back like that is why we're saving row and column here. So next row and next column will be what we use for the recursive call. So now we actually need to make next row and next column be the position of the next empty space. So what we're going to do is we're going to loop, and we'll have a condition in there. But essentially our loop is going to be advancing the scanner. So first it's going to go left to right, and that's all that is increasing the column number. But if we go off the right side of the grid, then that means that we need to loop around to the next row. So if we go over the maximum number of columns, which is just the length of a row, then we just need to go to the next row, that means, at the left side of the grid, so setting next column equal to 0. Now if we've gone all the way off the grid itself, that means that we've advanced past the bottom right hand corner. So we've filled the grid, that means. That's our condition where once we reach the bottom right corner, we know that we have filled the grid. So we'll have some special logic after we get out of this while loop that's doing that. So this code here is just advancing the scanner one step, and we have it in a loop. So it'll just keep going over and over and over. And we want to stop once we either have that condition where we fill the grid or we find an empty spot. So we want to keep going while we're on full spots. So we'll just check whether or not the grid position is equal to true. Once it's false, we find an empty spot, and it'll break out of this while loop. Then next row and next column will contain the actual position that we want. All right, so once we've got the scanner at the next spot, first let's check, did we fill up the grid? If we did, that means that this recursive call just placed the very last piece of our grid. So if we jump back to our solver right here, maybe we can get another one going. Here we go. So this is the recursive call here. So it's now going to place blue, so maybe we're in the blue for loop, and then it's advancing the scanner here. And it realized, oh, we got out of the while loop and got to the bottom right hand corner. That means that the piece that we just placed filled up it exactly once. So we're going to increase our ways filled, like we just saw in the top there, by 1, and then loop around in that for loop to the next piece. So that's exactly what we want to do. We just want to increase the ways filled counter by 1, and that's exactly it. We're just going to loop on to the next triomino after that. Now, if we didn't fill the grid, if we just found the next empty spot, this is going to be our recursive call. So we're going to call ourselves again, count triomino fittings, with our new grid. So we remember we've placed that triomino now. Our new next scanner position, which is at an empty spot. And then that's it. It'll try all the triominos at that next spot using our new version of the grid. And what we want to do with that result then, so this is going to return some numbers, probably some large number in most cases. We're going to add that to our tally for this particular call. So we'll do plus equals with the result of this recursive call. So yeah, so by the end of this, we'll have the correct ways filled tally for this particular triomino. The very last thing we need to do before we advance to checking the very next triomino is pick up the triomino that we just placed. So if we go look at this again, here we need to pick it up before we try to place that new black horizontal one. We need to pick up the cyan vertical bar. So we're going to make a method called remove triomino. We're going to remove it from the grid. We're going to remove it from the current position that we're at, and then we want to remove that triomino type. So this can be very similar to place triomino, but it's just going to be able to pick it right up without even doing any tests. So let's write that method really quick. So it's just going to be a void method. We don't care. There's no condition to return. It's just going to pick it up. There's no checking it needs to do. It's going to take in our grid and the triomino that we want to be picking up. All right, we're going to just copy paste the same code from before that calculated the positions of the triomino that we were trying to place. We're just going to copy paste that into the remove triomino because we're going to be using it again. Here we'll just do a return instead of return false. And then we'll also copy and paste the code that we did for placing the triomino and just change it to being it or picking it up. So we're just going to change all those positions to setting them to be empty instead of setting them to be full. So that's as simple as what remove triomino is. It's just like placing triomino, except we're setting things to false instead of true. And we don't have to do any checking because we're assuming that the triomino is there. All right, so at this point, we're almost done. We just need to return something. That's what this error message is up here doing. So at the very end of our for loop, our tally should be the correct tally. So we can just return ways filled. And we should have it returning correctly with all the recursive calls and everything. All right, so we should be done and we can do our tests now. All right, so I've got a list of test cases that I know the answers to. So let's just say that we'll have 10 test cases here. So let's just start with something easy. So a 1x2 grid, there's only 2 spots on it, so we can't fill it up. So this should return -1. Our scanner code changes any 0 results out of this count triomino fittings to -1 is like a signal that, hey, you gave us an invalid grid. It won't work at all. 1x3, so 1 row, 3 columns. This is just the horizontal bar piece. So there should only be a single way, just by placing that horizontal bar, to do it. And there we go, we got the right answer. 1x6, this is just 2 horizontal bars right next to each other, so that's still only one way, even though there's 2 different pieces. That's just one way to actually fill the grid. Cool. 2x3, the example that we gave on the solution prompt here, and we found that, hey, there's only 3 different ways to do it. Let's see if we get the right answer there. We do. And I've got a few other test cases. So 3x4 should be 23. We know that 6x6 should be 80,092. We know that 3x7 should be 441, yeah. And 6x7, ooh, so this one takes a little while. That took a second there. So 614,581. So now we're going to be moving on to the second part of the problem, because if you notice, if I try 6x8 here, which is the longest valid solution that we had in our test cases, it's going to take about 10 to 15 seconds here to actually calculate it. Oh, apparently even more than that. Holy cow. So this would actually fail in our competition because our runtime, we have a runtime constraint that will cut your solution off if it takes too long to run. So we need to now make our solution faster by making it more efficient. So we're going to be using the technique called memoization. The idea behind memoization is to save, so in some sort of data structure, solution or calculations that you've already made. So for us, this is calculating the number of ways to fill a triomino. So basically the output of this function, given a current state of the grid and the current scanner position. If we can somehow save in like some sort of just table where if we get this particular grid layout of which squares are empty and which squares are filled, no matter how we did those, like which triominoes went where, we don't care about that, just which were empty and which are filled. That's what this variable contains. And then which position the scanner is at. If we can somehow have a table that maps those things to the solution, then we should only ever have to calculate those things once. And when we get duplicates, which we know we will, because say the 2x3, we know that there's 3 ways to fill a 2x3 square. So any larger grid, which has a 2x3 portion, it's going to have to recalculate the same stuff for the same filled and empty spaces list. Like the answer for the non 2x3 portion of the larger grid is going to be the same no matter how we fill up this 2x3 essentially. So say that a 4x8 required like 100 more after you filled up this 2x3 portion. Then we know that it'll just be 100 times 3. 100 for this piece, 100 for this layout, 100 for this layout, 100 for this layout. So it will make our solution faster if we can just save some of the solutions or some of the outputs of this problem. So that's the big idea behind memoization. So the way that this is going to take place is we're going to have a map data structure. And it's going to map our inputs to our outputs. Now, you can't have 3 inputs in a map, unfortunately, in a Java map. You have to somehow summarize them all together into one input thing that can be represented as like some list of numbers or some number. And the summary algorithm, which you can also just call it like a hashing algorithm, the one that we're going to write is going to output it into a long data type. So this is just a larger int data type. It's double the bit size. So an int takes 32 binary numbers to express. A long takes 64. So we're going to be using a long, and I'll explain why we're using a long once we get to writing the hash portion. And then the output we know is an integer. We know that we have the int type right here is the output of our function. And we'll call this saved solutions, will be the name of our map. And we're going to stick in here the solutions that we come up with. And we're going to be using the hash map implementation of the map. There's many different kinds of maps that you can use. We're just going to use the hash map. There's also a tree map, I think, out there. There's loads of different ways, and they all store and retrieve data, these table entries, in various different ways that can be faster or slower. So you can experiment with these to see which one works best for our problem. So yeah. So the top level sort of abstract way that we're going to be using this is actually quite simple. First, we just have to generate that summary. So in some hash variable, we're going to have some method that will take in our inputs, grid, row, and column, and generate this summary. So this long here that is a unique thing for our inputs, but it's very concise. It's kept up all into one number, one long number. Then we're going to look up the solution, so check if we've actually even saved it. So the way that we can do that is by saying that the saved solution is savesolutions.get, and then passing in our key, our inputs. So if it is in the saved solutions, if we've already encountered this set of inputs before, saved solution will actually have a number. Otherwise, it will be null. So we'll do a null check here. If it's not equal to null, then we know we've already encountered it before, and we can just return that saved solution. If it is null, that means that we haven't encountered it before, and we haven't saved it in this map. So that means that we have to go on and do all this code, which actually does the calculation for us. And then at the very end of the calculation, we have to go the other way. We have to save the solution. So we've found what ways filled is for our specific inputs. So we'll bind our inputs, which are represented by hash, to our answer that we found, so ways filled. And that's all it is. We just have to write the hash state method, but the ways that the hashing and the map is used is quite simple. You summarize your inputs, check if you've seen it at all. If you have, you can just return what you found before, because it won't change. The answer isn't going to change for a specific grid, row, and column. Otherwise, calculate it, save it so that the future ones can just look it up again instead of having to recalculate it, and then return your answer. So that's all that the top level thing is. We just have to write this hash state algorithm now. Alright, so let's just write the head of our hash state method. So it's going to return along the hash, the summary of our inputs. It's going to take in the grid, the row, and the column. Now we have to make sure that our hashing algorithm is both fast and not too wasteful. If we don't have those two things, then it might even just be faster not to do this dynamic programming at all. Essentially, we might just be defeating the purpose if our hashing algorithm is too slow. We'll defeat the purpose of even having a hashing algorithm. The whole point of this thing is to save time. And if it's too slow or too wasteful or too inefficient, then we shouldn't even have it at all. So we have to make sure that our hashing algorithm is really efficient and concise. So the way that we're going to do this actually involves looking at one of our larger examples. So this is an 8-row by 6-column grid. And if we just advance a couple spots, so it's going to place a red, throw a blue in there, throw some more blues, and let's just stop here. So this is a potential spot in our algorithm. So we've just placed the red at row 4, column 3, and we filled up this part of the grid. So the algorithm doesn't see all these triangle pieces as we see them. It just sees trues and falses in the grid, if you remember. So everything above here is going to be true, some of these will be true, and everything below here is going to be false. So there's a very important thing to notice here. If we just jump over to Paint so I can show this off, because of the way that we've written our scanning algorithm, we never go past any empty spaces. So we can assume that everywhere before our scanner, or a place our scanner has been, we know that it's going to be full. So there's no point in storing that as a part of our hash. Remember, the hash just has to be unique for each grid and row and column. It doesn't have to store all the information about the grid, row, and column. We just have to have a unique number for each one. So that way we can look them up by their code, essentially. So we can essentially just block these ones out above the scanner. We know that everything above the scanner is filled. We don't have to worry about those at all. In addition, we know that all of the largest piece that we have vertically is our vertical bar, the cyan 3-row by 1-column piece. So this is the largest area, essentially, that we can have filled at this point. If the scanner is on this row, there's no way that we'll have any pieces down here. Like, we can't have a piece right here because we haven't gotten to this position yet. We go left to right, top to bottom. So the largest piece that we can have is maybe covering like that. So we don't have to worry about anywhere below down here. We can basically assume that everywhere down there, just like we assumed above, is empty. So we don't have to store this information in the hash once again, like before. All that we care about, everything that makes a current or any given grid, row, and column input set unique is just which position you're at with the scanner and the data inside these 3 different rows. So we just have to record the filled and empty positions of these 3 rows, the row on the scanner and then the 2 rows below. So that's what our hashing algorithm is going to do. So let's jump back to the code and get started on this. So we're going to be using some bit manipulation techniques to do this. We're going to start with a 0 hash, and you have to start thinking about these in terms of binary. So the current hash is 64 zeros in a row. And we just need to get all of the relevant information, the row, the column, and those 3 rows that we talked about. We have to get those somehow represented in this one number. So if we start with the row and column, each of those we can just pick the first, say, 8 bits of those. An 8-bit number goes up to 255, or 256 unique numbers. We're never going to have a grid larger than 255 rows or columns. That's way past the constraints that we have for the competition. So we just have to store the very first 8 bits of our number. So the way that we can do that, let's start with the row, is you can take the current hash and bitwise OR it with our row number, but cast to a byte. So by casting it to a byte, we are taking only the first 8 bits of the row. And by using OR, we're essentially saying any numbers on row you need to essentially write onto the hash. There's a little bit of hand waving there, but that's essentially the basics of it. Same for the column, but we're going to have to make sure that we don't overwrite the same 8 bits. So this line here will take the very first 8 bits of the row, the very lowest digits essentially in hash. It's going to assign those first 8 bits in hash to our row bits. We need to now shift over by 8 bits so that we don't overwrite row with our column bits. We need to have a different spot on the hash bit length dedicated to our column. And the way that we can do that is by doing a bit shift. So we'll bit shift left by 8 bits. And we bit shift to the left because we started on the right side of the number. Okay, so then our row and column have been stored, and we've only reached bit 16. So we still have 48 bits left to store our 3 rows. So that means up to 16 bits per row. So 16 essentially is going to be our maximum row length. That means we're imposing a little bit of a constraint here, but even 16 is past the constraints that we gave the students for the competition. So that's okay. So we're going to have this counter here, bit, which is keeping track of which bit we're on. And then we're going to go across all of the different spots in these 3 rows and write a 1 to the hash bit if the spot is filled, and then a 0, we'll just leave a 0 there if it was empty. And we'll just go across in order from left to right, top to bottom, across these 3 rows, and just write those bits. So the way that this is going to work is we'll do a loop through each of the 3 rows. We'll start at the row of the scanner. We'll go up through the 3rd row past the scanner, but we also want to make sure that we don't go past the edge of the grid. We don't want to go off the edge, and furthermore, we can just say that any rows, like if we're on the 2nd row from the bottom, we'll just say that 3rd row is all zeros. That's a way to summarize our current grid state then. And then we're just going by 1 row each time. And then we're going to write the entire column. So we'll start all the way on the left of the column and go all the way over to the right side of the column. So we'll go up through the length of our row. And we'll go over each column. And all our check is if that grid position is full, then we need to write a 1 at the current position. So that's going to be achieved by, once again, ORing with the hash a 1. Just like that. But we want to shift it over before we write it by how many bits we need it to be at. So the very first cell, essentially, this one right here, will be at bit 16 because bits 0 through 7 are for the row, 8 through 15 are for the column, so 16 will be whether or not this very first space is filled. And then all we need to do is also advance that bit counter so that the very next one goes on the next bit. So by the end of this for loop, we'll have recorded both the row, the column, and all of the spots in those 3 relevant rows, the information that we need to make a unique number for each grid, row, and column setup. So then we can just return that hash. And there we go. We should have a working solution now that it will come up with a table of the inputs of our count trinomial fittings rec function and binds them to, in memory, the solution. So we don't have to recalculate them every time, which takes a lot of time. And hopefully our hashing thing is faster than that. And I've just discovered one mistake that I made during this. We have to make sure that we cast this 1 to a long type first. If you just write a 1 in Java, it just assumes that you're using an integer type. But we're going past 32 bits when we shift here. So if we fail to cast it to a long first, that 1's just going to go past 32 bits and just become a complete 0. We have to make sure that we give it enough bits to shift through before we actually do the OR. So if we test this out now, we'll run the program. Let's just say 10 inputs. We can just test a few of them to make sure that we're still getting the right answers. 1 by 6. So let's try one of those larger ones that we had. Oh, what's going wrong here? I'm not sure what just happened there, but I got it running again. I didn't even change anything. It must have just been a little fluke there, but yeah, we have the right answers now. So we just had to rerun it. So 1 by 2 still gives us -1. 1 by 3. Oh goodness, what's going on? I know what we have to do. So we aren't clearing out our saved solutions between each run. Remember that we need to empty all of these calculations because the hashing might give the same answers for the different grids that we give between 2 different test cases. So we're going to do a save solutions.clear before each of our things. That way we start with a fresh map, a fresh table, and we make sure that we aren't reusing solutions from previous runs because the hashing might be incorrect for the same grids. Alright, so let's try those again. Here we go. So 1 by 3 gives us 1, 1 by 6 gives us 1, 2 by 3 still gives us 3, 2 by 4 gives us -1, 3 by 4, 3 by 34, whoops. That one's still a little bit too big for us. 3 by 4 gives us 23. But, and most importantly, 6 by 8 now gives us it in like less than a second. Before it was about 10 seconds. We can probably go even higher now. 6 by 9 is working. 6 by 10, still super fast. So our dynamic programming has significantly increased our speed of our function while still giving us the correct answers. And this is very important for our competition where we had that runtime constraint, especially for Python. If you use the Python language for our competition, Python's even worse in doing the data structures testing, so reading from the data structure, doing comparisons, and writing the data structures. They're a little bit worse than Java, so they go even slower. The 6 by 8 maybe takes like a minute in Python if you don't have dynamic programming. So there we go. That's our whole solution for question 8, triominoes. Thank you for watching the solution videos. This is the last one, as it was the last problem. We hope that these have been informative, and we hope to see you again at our future competitions.